Hello everybody, good morning, good afternoon, good evening, and wherever you may be watching this. This is another video coming towards the end of our integration chapter. So here I'm going to show you something I've held off from doing actually, which is showing you how to integrate using the ClassWiz calculator for definite integrals. So use that with caution. I don't want that to be a sidestep of your understanding. Also as well, I'm going to try and prove to you why integration works using a different approach, but just remember the take-home points are that when we integrate, we can do that to find areas underneath curves. So we'll come to that in due course. First of all, you can guess, no doubt, we're going to have 4 warm-up questions, which are here. So have a go at these first, if you can do, please. After you've attempted the questions, do press play, and then I'll talk you through the solutions together. Okay, so I'm going to do the solutions now, so get ready and compare your results to mine. So question 1, we need to find the integral of t squared dt from x to 0. Now usually integrals are with respect to x, but to be honest they can be with respect to anything. We could have had z squared dz, or could have had p squared dp. It doesn't really matter as long as what we're integrating is with respect to what's here. And so now we should know that when we integrate a function t squared, we take the power up one and divide through by the new power. So t squared becomes t cubed, and then we divide through by 3. And so we get 1/3 t cubed between the limits of x and 0. And so we have 1/3, substitute x for t, that gives us 1/3 x cubed minus 0, which is obviously just 1/3 x cubed. So we're going to mention this later on in proving why integration works using a different sort of approach. So we'll come up to question 1, but that's question 1 done, a nice easy starter. Question 2, prove from first principles that the derivative of 1/3 x cubed is x squared. So what we need to do here is to recall the definition of the gradient function. The gradient function is the limit as h goes towards 0 of f of x plus h minus f of x all over h. So if we have a look here, what is f of x? Whatever our input x is, we cube it and then divide it all by 3. And so let's just put in our case, what f of x is. So as I say here, what we're doing is we're doing 1/3 of the cube of the input. So if input is x plus h, that's going to be 1/3 of x plus h all cubed. F of x is just 1/3 x cubed. All of that divide through by h. Now what I'm going to do here is make a suggestion, but because we have a common factor of 1/3, we just put that 1/3 to the bottom and make it 3h. Now I know writing the limit h goes towards 0 is a drag, but it is important. That becomes 3h. On the top we have x plus h cubed minus x cubed. We've just taken out that common factor of 1/3 and put it on the bottom. It's a bit more space we need. So now we can actually expand this bracket and then simplify out. So if we expand x plus h cubed, you could even use a binomial expansion for this, doesn't really matter, but you'd have x cubed plus 3 lots of x squared h plus 3 lots of x h squared, then plus h cubed, then minus x cubed, all over 3h. Now if we look closely at the beginning and end terms on the top, this x cubed here will cancel with this minus x cubed over there. And so what we'll have now is we can divide through some of these terms by the 3h on the bottom. So for this term here, 3 divided by 3 cancels, the h's cancel, we're just going to be left with x squared. This one, the 3's again cancel, 1h will cancel, so h squared divided by h will give us h, and we have an x. So we have xh here. and then h cubed divided by 3h. Well, one of the h's will cancel, give us h squared, divided by 3 gives us 1/3 h squared. We can now evaluate this limit as h goes towards 0. So as h goes towards 0, xh will go to 0 as well. H will pull it down to nothing, and h squared will become close to 0 times 0, which is 0. And so these two terms at the end will vanish to nothing, and we're just left with x squared, which is exactly what we wanted to prove. So the limit of the derivative function, the gradient function of 1/3 x cubed, is x squared. Question 3, calculate the area under the straight line graph here, where y is x plus 2. Now, we could just do this using the area of a trapezium. In fact, if you want to do that, you absolutely can do, that's fine. The question doesn't state it, but I'm just going to show you how you can do this using integration. So what we have here is we need to integrate between the limits of 4 and 2 of y dx. So that's x plus 2 dx. And so we take the x power up 1 and divide through by the new power. So x becomes x squared over 2, or half x squared, and the 2 just becomes 2x. Remember, when we have a constant and we integrate it, we just put the variable on the end of that constant. So if it was 1, it'd be 1x. If it was 7, it'd be 7x. Anyway, our limits are between 4 and 2. Now, I'm going to show you how to do this on ClassWiz, so this is a big reveal in a second. Again, I don't really feel too comfortable with the fact that ClassWiz can do everything like this, but I'm sure you'll love what I'm going to show you in a moment. Anyway, doing it without a calculator. So half x squared, when x is 4, is a half times 4 squared. So half of 16 is 8, plus 2 lots of 4. 2 times 4 is 8. We're going to minus from that, when x is 2, half of 2 squared. Well, half of 2 squared is half of 4, which is 2. Then 2 times 2 gives us 4. So this is going to be 16 minus 6, which gives us an area of 10. So you're probably asking, okay, Mr. Bailey, how do you integrate using a calculator? How can I get the ClassWiz to do the hard work for me? Okay, well, I'll show you. Okay, so what we do here is we can press this integral button here. Okay, in this bit, we put in our function of x. So our function in our case is x plus 2. To get the x, we're going to press alpha and then the bracket, then plus 2. Now we need to toggle back, there it was, to put in our limits. So our lower limit was 2. And the upper limit was 4. Press equals. It couldn't be simpler, could it? Look at that, it's like magic. I think it's too easy. Maybe I'm an old-fashioned misery person, but anyway, there you go. That's a great thing. So you can calculate, it can really save you bacon if you know how to use it, but don't be overly reliant on your calculator. You need to know what's happening behind the scenes and have this understanding. This is why I've only shown you this now, rather than in one of the earlier lessons. Anyway, that's question 3 of the warm-up completed. Question 4, we've got a bias dice created such that the probability of rolling a 6 is 0.2, so that's slightly above 1/6. Find the probability that after a total of 20 trials, the number of 6s rolled was at least 2, but less than 6. So I've not said here, what you need to remember and realise is this is a binomial distribution. Okay, if you roll a dice, you can think of it as either ending up on a 6 or not a 6. So it's 2 outcomes only, in a sense. The chance of rolling a 6 is 0.2, it's fixed. It meets all the criteria of a binomial distribution. And we can also safely assume that each roll of a dice is independent from future rolls and previous rolls. So what I'm going to do here is just remind us that this is going to follow a binomial distribution. The number of trials is 20. Probability of success, probability of getting a 6 is 0.2. Okay, and we're wanting here the probability that after 20 trials, the number of 6s rolled was at least 2, but less than 6. And so what this is saying here is we want the probability of the number of 6s being less than 6, so that's the same as saying up to and including 5, and at least 2 is saying this. So that's how we put it into our calculator-friendly language. Okay, so now we can manipulate this and calculate it. And so this is the same as saying it's a probability that x is anything up to and including 5 minus a probability that x was everything up to and including 1. If we just did this bit, that would be 0, 1, 2, 3, 4, or 5, but we're not interested in 0 or 1. That's why we need to take away this bit here. So now we can use the ClassWiz binomial CD function. So just to remind you, it's been a while since we've done this in class, been a while since we've done anything in class. If you're aware of what's going on, which I'm sure you've heard there's sort of a virus going on, you press menu, then we go to 7, so press menu 7, scroll down, binomial CD is this one. Press 2 for variable. And so x is what we're interested in. So the first thing is 5 successes. N, number of trials, is 20. Probability of success is 0.2. So we give answers to 3 significant figures. For now, give it to 4 before we round off. So that one is 0.8042. So give it to, say, 4 decimal places now. And this one here, we can just press AC to toggle back, and we can change this value of x to 1. Do that, and we get 0.0692 rounded off. So 0.0692. And so if we just do this calculation, go back to normal mode, press menu and 1, 0.8042 minus 0.0692 gives us 147 over 200, which is 0.735. So that's just telling us if we had 20 rolls, we're pretty likely, sort of about 74% likely, to get either a 2, 3, 4, or 5 for your total number of 6s out of 20. Okay, so this is trying to show you why integration works. I can't stress this enough. This isn't going to be tested, okay? This method for integrating, approximating integrals, and taking the limit, this is not going to be tested, so don't worry. This is just to try and help your understanding along. Okay, if you're not entirely sure what's going on, it's not the end of the world. I don't want that to sound negative, but don't get too het up, don't get too stressed out about what I'm going to show you here. This is just trying to show you why it works. The take-home point is just when you integrate, it gives you the area underneath the curve. So this is just an explanation. Okay, so we're going to prove the result from warm-up question 1, and we can use this result here. The sum of the first n square numbers is this result here. Okay, so if you're thinking, well, why is that the case? Does that really work? I'm going to show you in a link on this video, if you want to click on that, this result. I'm going to prove that this is the case, but for now I'm not going to go into it. If you want to see how this works, click on the link from the video. Either if you see a link on the screen, click on that. If you don't, click on a link I'm going to leave you in the comments. But for now, we can assume this result. So, how does this work? What does it all mean? So if I just take you forward, here's a curve of y equals t squared. So same idea if it were x squared, but instead of x-axis, we now have a t-axis. Okay, so we want to work out this area underneath the curve. Well, one way we can approximate that is to imagine rectangular strips going along the bottom of the curve and then adding up the areas of those. So we could have something like this here. So as you can see, if we were to add up these rectangular areas, it wouldn't give us quite the area underneath a curve. It'd be an overestimate because we've got these bits here above a curve. So it's not an exact area, but it's not far off really, I hope you can see. If I added up all of these, it gives us a rough and ready approximation for the area underneath this curve between 0 and where t is x. So what I've done here, I've done 13 strips. Okay, I've done 13 rectangles. That one you can barely see because it's so low. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Okay, so hopefully you can see that there's 13 strips here. So I'm going to show you how we can think of this. So if we've got 13 strips, we can actually work out the area of each strip in a way. But first of all, what we need to do is work out the width. So if we have 13 strips, I'm going to say the width of each one, 13 uniform width strips. I'm going to say this is delta t. So imagine the width of each one is delta t. Well, from 0 to x, that's a total width of x, and that's been divided between the 13 strips. And so each width, delta t, is this distance from 0 to x here, which is x, divided by the number of strips I'm using, which is 13. I'm going to show you the general case in a moment. But for this particular case of 13 strips, if you're thinking, why did he choose 13? Well, good question. I could have chose 12, 11, 10, 20, but I just happened to fit in 13 using this width I used. It doesn't matter this particular number, but just humour me for a second. Imagine it was 13. Okay, so what we can say here is the area underneath the curve, the area under this curve is approximately equal to the total area of the 13 strips. I'm going to generalize this to n strips in a moment, so we'll get the general case and then the general result. So the total area of all these strips. So what this is going to be, it's going to be the width of each strip. So for example, the first one will be the width of the strip, which will be delta t, then multiplied, in fact I'm going to write this a different way. I'm going to put the height first. So the height of each strip will be the function of that value. So if we've got, for example, x, the height of it will be f of x, which will be x squared. So first of all, the height of it is going to be the function value at that particular point. So this first one is going to be a function of x over 13. That'll give you the height of this first tiny one. That's the height of the first one. And the area of a rectangle, of course, is the height multiplied by the width, which we're calling delta t. The next strip here, okay, that's going to have a height of the function of 2x over 13. So that's going to be 2x over 13 all squared. But for now, I'm just going to leave it as f of 2x over 13. That's the height of it. And we're going to multiply that by the width, which again is delta t. The next one, I'll have a height of, which is f of 3x over 13. Hopefully you can see the pattern now. Multiplied by delta t, plus so on and so on and so on, until eventually we have f of, over here, I've wrote this as 13x over 13, which is obviously just going to be f of x, because here t is x, but I've left it as 13 over 13, just so you can see the pattern. So then it's 13x, I'm never leaving myself enough space, multiplied by delta t. Okay, so we can neaten this up slightly. So we said the width was delta t, but delta t is just x over 13. I don't know if you can hear that. That's Tallulah the cat. Hello, Tallulah. She's wrecking the video. Never mind. Anyway, delta t is x over 13. And so we can say that, therefore, the area, we can factorise out this delta t because this is common to each strip. So the total area is going to be x over 13. Then it's the sum of from k, where k is just a dummy variable, from k equals 1 up to the total number of strips, which is 13, f of kx over 13. And so that's going to be the area approximately anyway. And so what we're going to do here, we're going to take this result and then generalise it when it's not just 13 strips or 10 strips, but for n strips. So just take this result here and imagine it's for n strips. So what we have, we're going to have the area is approximately equal to x, before we had x over 13, just go back, because we had 13 strips. If we have n strips, that just becomes x over n. Then we're going to have a sum from k equals 1 up to what used to be 13. That's now going to be up to the nth strip, the final strip. F of kx, before it was over 13, now it's going to be kx over n. Now we need to remember what f was. So f of x was just x squared. So f of t is t squared. So x over n, this is a summation. It's going to be from k equals 1 to n. Just to repeat, this is just explanation. You don't need to panic about seeing this in the exam, but if you understand it, it will help in case you get given a bit of a trick question. So from from k equals 1 to n, f of kx over n is just all of this squared. So it's going to be k squared x squared all over n squared. Now we can neaten this up. K is varying from k being the first, the second, the third, the fourth, all the way up to the nth strip. But here, our variable is t. X is just the endpoint in this case. And so x is a fixed constant for this example, and n is a fixed constant too. N is just the number of strips. And so x squared and n squared are going to be constants, and they're going to be a constant factor in all of these sums. So what we can do, we can factorise out this x squared and the n squared. This is going to be constant for each and every sum. We can factorise out this and put it on the outside of the sum. So if we do that, x squared over n squared multiplied by this, well, x times x squared gives us x cubed. Then here we have n cubed, and that's going to be the sum from k being 1 to k being n of just k squared. So k is going to be 1, 2, 3, 4. K is going to be a whole number, therefore k squared is going to be a square number. And so what this here is, this is going to be the sum of the first n square numbers. This is going to be the sum of 1 squared plus 2 squared plus 3 squared, all the way up to n squared. So now we need to remember that result from before. So we have x cubed over n cubed, and the sum of the first n square numbers from before was 1/3 n cubed plus a half n squared plus 1/6 n. So all I've done here is I've used that result from before and said that the sum, it's just a fancy way of writing the sum of the first n square numbers. That becomes this. Okay. Now it's a bit of an ugly looking bracket, but we can use what we know about brackets already, and we can expand this out. And so if we expand out this term with that one, and also with that one, we can neaten up this result. So x cubed over n cubed multiplied by a third n cubed. Well, this first one, the n cubed, is going to cancel on the top and the bottom. And so what we're left with here is going to be 1/3 x cubed. The next term is going to be the n squared will cancel with 2 n's on the bottom, but we'll still have an n left on the bottom. So that's going to be 1/2n that's going to be x cubed. And then we're going to have 1/6 n squared x cubed. And so this area is going to be approximately equal to this thing here. So the area is approximately equal to this result down here. So how does that help us in any way, shape or form? Well, we can see that the area, as you'd imagine, is dependent on the number of strips. That sort of makes sense, doesn't it? That the area would have n in it somehow. The number of strips will depend on our approximation of the area. That makes sense. So let's just take this result one step forward. How would the number of strips affect it? Well, this is a little animation here. Imagine the number of strips increasing and increasing, and compare it to the actual area underneath the curve. So hopefully you can see here, when the number of strips is small, the approximation is very crude. But as the number of strips becomes greater and greater, here for example, oh, just missed it, the approximation becomes more and more exact. And if you increased the number of strips so it approached infinity, the area would indeed be exact. 2, 4, 8, 16, 32, 64 strips. 128, it's pretty much exactly the right area. So what I can say here is, it's actually a limit. And so our result here, for the area, will be greater and greater increased in accuracy as n goes towards infinity. So we can say that the area under our curve is the limit as n goes towards infinity of 1/3 x cubed plus 1/2n x cubed plus 1/6n squared x cubed. So as n goes towards infinity, this term here is going to vanish because 1/2 lots of infinity, if that was such a thing, would be nothing. And this here, the reciprocal of something approaching infinity, would again go towards 0. And so the only thing we'll be left with is the term independent of n, which is this here. And so the absolute limit of this area, as the number of strips approaches infinity, is 1/3 x cubed, which is what we wanted to prove. And that, I think, is a very robust, very convincing argument. So it does work, this integration, Lark. That's the area underneath the curve of y equals t squared from 0 to x. A few more things. So generally speaking, we did that from 0 to x, but generally, where f is continuous on an interval from a to b, continuous means differentiable everywhere, and we have these little elements, xi, where each xi is between a and b, we can consider the area being the limit as n goes towards infinity of the area of each individual element from x1 to x2 to x3 all the way up to the nth strip. If we sum up these tiny, tiny strips, as number of strips approaches infinity, it becomes one and the same thing as the integral of the function between these limits b and the limits a. And so the main result I've put in here for you. And so as n goes towards infinity, these delta x's become dx's, and we get the exact sum. So rather than this sum here, it becomes the integral summation symbol. So generally, delta x is the width of each of the n uniform strips, uniform in terms of the same width, each one. So if we have n strips between A and B, generally speaking, not just between 0 and B, the width of each strip will be the distance between B and A, divided by the number of strips. So each dx will be b minus a over n. In our example, the width was x because our b was little x and we started from 0, so we had x over n, but this is the general case for the width of each strip. This gives us another result though. So because we defined delta x as b minus a over n, you can see here that as n goes towards infinity, delta x will go towards 0. And so we can think of this in terms of another limit, not a limit in terms of n, but a limit in terms of delta x. And so the area of all the strips as delta x approaches 0 is the summation between b and a of a function multiplied by delta x, which becomes the actual integral between the two limits b and a. Okay, if you're wondering why I bothered doing all of that explanation and thinking, well, that was just an awful lot of guff, why did he bother? This is an actual question from 2019, and it absolutely freaked the whole load of people doing the exam out. You know, the Twitterati took to social media. How could they set that question? They've wrecked my life. This is awful. This is the worst thing in the world that's ever happened in the history of mankind, ever. Well, maybe not quite that, but there was an awful lot of blowback from this, and people really didn't like the question. But if you understood what I was saying previously, you'll see the link, you'll get the concept, and you realise, aha, this is actually a dead easy question. If you understand this concept, you could have done this question in literally about 10 seconds using a class whiz. Anyway, it's saying here you've got y equal to the square root of x. This is a diagram. You've got a point P on the curve. That point P happens to not matter at all. The shaded rectangle shown above has height y and width delta x. Calculate the limit as delta x goes to 0, root x delta x, that's y delta x. So y dx is the area of each strip, okay? So as delta x goes towards 0, the strips get smaller and more numerous, and this region from 4 to 9 would have more strips filling it, and the area would be more precise. To stop mucking around and cut to the chase, this thing here, based on what I mentioned before, is one and the same thing. As dx goes towards 0, it's the same as the integral from 9 to 4 of the square root of x with respect to x. Okay, but just bear in mind, root x as a power is x to the power a half. So in the limit as delta x goes towards 0, it becomes a calculus question, becomes an integral. So now you know that, it's dead easy. So we take the power up, so a half becomes 3 over 2, and we divide by the new power. So dividing by 3 over 2 is the same as multiplying by 2 over 3. So it becomes 2/3 x to the 3 over 2 between these limits of 9 and 4. So if we plug in these limits, so we have 2/3 times 9 to the 3 over 2, then minus off 2/3 times 4 to the 3 over 2. This is the longer way of doing it as well. I'm going to show you how you can do it with the class whiz. But anyhow, just showing you how to do it here. So menu 1, move it over. So we've got, first of all, 2/3 multiplied by 9 to the power 3 over 2, close bracket. We're going to subtract, oh no, not that bracket, move along, that's it. Then minus off 2/3 multiplied by 4 to the power 3 over 2. and we get 38 over 3. That is the area in the limit as delta x goes towards 0. And so all this question was just a test of understanding. If it was given to you like this, it'd be too easy. It wasn't testing your calculation skills, it was testing your conceptual solidity. It was testing how well you knew it. So I did say you could do this in about 10 seconds. Okay, so put your watch on me. Go. Oh, this here, dx goes towards 0. That's an integral. I'm going to get my class whiz out. I'm going to go press this button here. Root x. So you type in square root x. My limits are 9 and 4. So toggle back, put 9, put 4, press equals, 38 over 3. How easy was that? Okay, it might have been 14 seconds or 15 seconds, but you can appreciate once you know the concept, it makes it dead easy. So it's not just about plugging in the numbers, you need to understand what's being talked through in these notes as well. If that actually happened, hopefully you can see now, with a bit of extra time spent on your notes, understanding it, digesting it, it saves you an awful lot of marks in the exam, and a lot of grief as well. Okay, so that's that past exam paper question done. Next bit of this session, I need to just mention briefly how to calculate areas where the curve goes below the x-axis. Okay, so far, like I'm saying here, we've only dealt with areas underneath curves where the curves themselves are above the x-axis. So when you work out a area underneath the x-axis, it actually comes out with a negative value. Okay, so the area below the x-axis is going to be just the size of the negative result. So for example, if you integrate something below the axis and you get, for example, -4 or -5, that means the area of it is 5. Now, doing this here, if you're integrating below the x-axis, you need to do a really good sketch of the curve. Okay, so you need to sketch the curve. That's absolutely essential. Then you integrate it piecemeal, which means in parts, between the boundaries. So it's going to be easy if I just show you an example. 2 examples, in fact. First example. Calculate the area bounded between the curve y equals x squared minus 5x plus 6 and the x-axis. So here what we need to do is we just do this curve and factorize if we possibly can. I'm hoping you can see that we definitely can factorize this one. Okay, so that becomes -2 in brackets and -3. And so if we were to sketch y equals brackets x minus 2, brackets x minus 3, we'd have something that looks a bit like this. Now, again, I do apologise for my awful curve sketching ability. Here goes nothing. Absolutely awful, but please do forgive me. Anyway, so this will intercept the x-axis at 2 and 3, and this y-axis intercept would be 6. Not that we need to worry about this. So the area bounded between the curve and the x-axis, we're talking about this region here. So I'm just going to call that region A. So if you consider region A, where region A is what I've called in there, that yellow bit, then we can see that this is going to be relating to the integral between 3 and 2 of y with respect to x. So that's going to be the integral x squared minus 5x plus 6 with respect to x. So if we integrate this, so 2 becomes 3, divide through by 3, so x squared becomes 1/3 x cubed, minus 5x becomes minus 5 over 2, x to the power 2, and the plus 6 becomes plus 6x. And we do that between the limits of 3 and 2. So again, I'll show you the class whiz way in a moment afterwards. Just to sort of speed along, as it were, you could do this on a calculator, that's absolutely fine. 1/3 x cubed where x is 3, that's going to give us 9, minus 5 over 2 times 3 squared, that's going to be minus 45 over 2, plus 6x, plus 6 times 3 gives us plus 18. We're going to minus off, when x is 2, 1/3 times 2 cubed gives us 8/3. Minus 5 over 2 times 2 squared, 5 over 2 times 4, that gives us minus 10. Then plus 6x, plus 6 times 2, that's plus 12. So if we key this in, here's what we get. So first of all, 9 minus 45 over 2 plus 18 minus off 8/3 minus 10 plus 12. That gives us minus a sixth. Now at first, this might throw you off or freak you out. How can it be a negative? You might be thinking. Well, as long as you just spot that this area is entirely underneath the x-axis, then all we need to do now is interpret the size of negative 1 over 6. It's the same, for example, as when you're thinking about the magnitude of a velocity. If a velocity was minus 1/6, the speed would be 1/6. So we just take the size of this. So the size of minus 1/6 is just 1/6. So therefore the area underneath that curve is going to be 1/6. Okay, if we've got a negative area, or an area below the curve, it's the same as integrating the negative integral. Remember, minus multiplied by minus gives us a plus. But until we get to that stage of understanding, I'd say to just do it piecemeal and then think about it in parts. Example 2. Sketch the curve with equation y equals x, brackets x plus 3, brackets x minus 5, and find the area of a finite region bounded by the curve and the x-axis. Oh, yes, I forgot to show you using a calculator for the previous example. Just quickly, before I do question 2, I'll just show you for question, works example 1. We had x squared minus 5x plus 6, and our limits were from 2 and 3. It's taking me ages to get to 3. Oh, there it was. So yeah, minus 1 over 6, which becomes 1/6. So anyway, I'm going to show you this one here. So we've got this curve, y equals x, brackets x plus 3, brackets x minus 5, and the area of a finite region bounded by the curve and the x-axis. So first of all, definitely do a sketch. Okay, so this will cross the x-axis at 0, minus 3 and positive 5. And it'll cross the y-axis at 0 as well. So it'll cross at 0, 0. And so this one here is going to look something a bit like this. And back up again. So that's going to be 3. And that'll be 5. And so we need to integrate in 2 separate parts now. We need to find this area here. Oops, that's a bit too big. Yeah, we need to find this area here between 3 and 0. We also need to find this region here in between 0 and 5. So we need to do this piecemeal. Region 1, then region 2, and then add them together to get the total area. So if I just call this, first of all, the yellow region A, and that region B. So first of all, just considering region A. Okay, so for region A, we're going to integrate between the limits 3 and 0. So between 3 and 0 of this function here. Now, what we need to do here is to actually expand out this function. And so that gives us, well, x plus 3, x minus 5. Expand that out, we get x squared plus 3 and minus 5, that's minus 2x's. And 3 multiplied by minus 5 gives us minus 15. Then multiply all of this on the inside by the x on the outside, gives us x cubed minus 2x squared minus 15x. So that's what we're going to be integrating between 3 and 0. So x cubed minus 2x squared minus 15x with respect to x. So again, just the same deal as before. Increase the powers by 1, divide through by the new powers. So x cubed becomes x4 over 4, quarter x to the power 4. 2x squared becomes 2x cubed over 3, and so we get minus 2 over 3. X cubed minus 15x becomes minus 15 over 2 x squared. Now we're going to integrate this between the definite limits 3 and 0. And so first of all, for this one, we're going to have, starting at, oh dear, hold on. Okay, bear with me a second. I didn't mean between 3 and 0, that was a minus 3, isn't it? Silly mistake yet again. Okay, so, apologise for that. Okay, the limits here are from 0 and minus 3. That's a minus 3. That's my fault for not annotating that. Okay, big apologies. Yeah, so that's minus 3 and that's 0. So we're going to integrate between 0 and minus 3. And then what we'd have, substitute in 0 here, just gives us 0 all along. And then minus, we substitute in minus 3. So a quarter multiplied by minus 3 to the power 4, that's going to give us 81 over 4. And then minus 2/3 multiplied by minus 3 all cubed, that would actually give us plus 18. Minus 3 cubed is minus 27. Minus times minus gives us a plus. 27 divided by 3 is 9. Times 2 gives us 18. Then the last term, minus 15 over 2 multiplied by 9, that gives us minus 135 over 2. Again, don't take my word for it. I've worked these out before. Do use a calculator, for God's sake. And so that gives us a total area of 117 over 4. Okay, so that's region A. Now we need to find region B. So for region B, for green area, what we need to do is integrate between the limits of 5 and 0. The same function. X cubed minus 2x squared minus 15x dx. So we've done the hard work. We know it's going to be this function here. So a quarter x to the power 4 minus 2/3 x cubed minus 15 over 2 x squared between the limits of 5 and 0. So substitute in x being 5 into this. Again, don't take my word for it, do it on a calculator. We get 625 over 4. 5 to the power 4 is 625. Then minus 2/3 times 125, that gives us minus 250 over 3. Then minus 15 over 2 times 5 squared, so that's 15 times 25 all over 2, that gives us 375 over 2. Then minus, if you chuck in 0, that just gives us 0. Now this thing here comes out and gives us a negative value. So that comes out at a really awkward looking value of minus 1375 over 12. But if you look here, that's because that's below the x-axis. Okay, so actually the area of region B is going to be this, but positive. So that's going to be 1375, positive 1375 over 12. Okay, now we can do the final bit and add up A plus B. So therefore, the total bounded area, is region A, which is 117 over 4, then plus 1375 over 12. So if you add these two bits together, I'll show you how to do it carefully with a class whiz as well. 117 over 4 plus 1375 over 12. That gives us a total exact area of 863 over 6. We can leave this in exact form here. We don't need to round it to significant figures. I'd say to give these an exact form if and where possible, unless a question says otherwise. So how to do this with a class whiz without running into any mistakes. So I'll show you how to do this now. Okay, so that is the total area, by the way. We've done the question, so if you want to switch off now, you can, and try the questions I've set you. So that's the final answer. Now on a class whiz, if I just scroll up for a moment, what I'll suggest with a class whiz is type the function as it appears, just to undo any way of you making an arithmetic error. So put the function in like it looks here into your class whiz. So press the integral button. Okay, this function is x, so alpha x, brackets, x minus 3, close brackets, new bracket, alpha x minus 5. So type in the function exactly as it appears in the question if you can, and do this between the two separate limits. Just bear in mind, if you try between minus 3 and 5, it'll merge a positive area and a negative area together. I'll show you what will happen. So if you try the lower limit as minus 3 and the upper one as being 5, you get a complete mess. You get it all wrong. So you still need to do it step by step, one area and then another, even with the class whiz. Otherwise, a class whiz will get confused about the positive and the negative. So what you need to do on a class whiz is to do it in parts. So first of all, this region here is between 0 and 3. Minus 3, rather. So type that in. Between 0 and minus 3. Make this into a positive. Oh, look. X plus 3. It should be, I put x minus 3. Second mistake. But I'm going to leave a mistake in this time. So x plus 3. So if we try this between 0 and minus 3, we get that. So write that one down. Then what you'd need to do is to do the same between the limits of 5 and 0. Just toggle back and put the limits in. So that now becomes I'm making a pig 0 of this. There we go. So that becomes the lower limit is 0, and the upper limit needs to be 5. Oh, got there eventually. So between 5 and 0, Oops. There we go. Now, you write this down, but make it positive. And then we do the first answer plus this positive answer to get the answer we needed. So again, with a class quiz, you can do it and it's easier, but it takes practice, need to take care. Okay, so that's just a quick run through of how you work out negative regions, areas beneath the x-axis. So think about it piecemeal and do a sketch and work out each area separately. So really important, you need to practice now these questions. So turn to page 299, finish off exercise 13E from the other day, and then move on to exercise 13F, try all questions. Do them step by step. Each time you do a question, check the answer immediately in the answers on the back of the book. Do one, check one. If you've got it wrong, think why you've gone wrong. If you're still unsure, please, please, please do email me or leave me a comment in the comment section. Okay, that was quite hard going, I know that, but thanks for listening, getting to the end of the video. I'll see you again soon, next time. Thank you very much.